We're going to be working on doing problems on aldehydes and ketones. So, and here we need to remember that the reactions of aldehydes and ketones are nucleophilic additions. Nucleophilic addition. That is, the reagent is going to be the nucleophile. Let's see what the nucleophile is. So here's a ketone, and here this is lithium aluminum hydride. Here the nucleophile is, you have 4 H's in your lithium aluminum hydride. That's negative, formal negative counter ion is lithium. So what you will have here is a nucleophilic attack. When you have a strong nucleophile, such as the hydride, and here, Grignard, this reaction proceeds through nucleophilic attack first, and then a proton transfer step. So, and I say that knowing the mechanism, knowing why these things happen, how they happen, it helps you a lot to predict products, which is ultimately your goal in these problems. So now, your nucleophile is going to be a hydride, so I'm going to transfer this from here to here. And what you're going to be forming initially, let's throw it in the back here. I'm going to have, here, you're going to have O negative. Here, you're going to have a metal, and of course, you have transfer a hydride. That's the one that I just transferred. The second step is just to do a proton transfer and protonate this. So your final answer is these alcohol. So notice you transfer one hydride. That's your nucleophile. So when you have, let me do the bottom one because it's the same reagent. So we have lithium aluminum hydride. Can be written also as lithium aluminum hydride, so more explicitly. And that's the structure. So your nucleophile is going to be the same here. So we're going to now transfer one hydride and just going to do another arrow from one of the H's, one hydride, and we're going to go. Well, now let me I'm going to go back here because the result of this will depend whether we have an excess or we have one equivalent. And that's a good point here because lithium aluminum hydride is a strong base, also strong nucleophile. So if you have, say, one equivalent of lithium aluminum hydride, what you're going to be seeing is just the acid-base reaction. So your product is going to be simply the conjugate base of the carboxylic acid. But now to reduce carboxylic acid, and lithium aluminum hydride is capable of reducing aldehydes, ketones, ester, acid halides, anhydrides, nitriles, amides, a lot. But to reduce this further, so after the acid base, we need an excess. So if you have an excess of lithium aluminum hydride, then this is capable of reducing the ketone and also the carboxylic acid. So if you have here that you're treating this with an excess, the answer is going to be different. In that case, you will reduce the ketone to the secondary alcohol and the carboxylic acid to a primary alcohol. And again, I was missing these bonds. But no, that's not right because I cannot have 5 bonds here, though. My mistake was made in the original structure. Oh, my God. Yay. So I cannot have those. Remember that you cannot exceed the octet. So that's like a cyclohexanone. All right. So in excess, you will be able to have the reduction of both the ketone to the secondary alcohol, the ketone to the secondary alcohol, and the carboxylic acid to a primary alcohol. So one equivalent, you just do the acid-base reaction. So strong base will remove that H over there. Okay, the last reaction that I have here is Grignard, and for that, I'm just going to remove this And now understanding what is the nucleophile here. So when you're treating this with phenyl magnesium bromide, and so what we do to make the phenyl magnesium bromide, what we have is the reaction of the alkyl halide with magnesium. So you will start here with bromobenzene, and when you put it with magnesium and say dry ether, you will make the reagent that's there. So I'm going to have phenyl magnesium bromide. And what it does, this is essentially, we can write this as an intimate ion pair. So I'm going to do this. And now that's a powerful nucleophile. And what do we do next? So I think I've erased something here. Oh, that I shouldn't have. So that had this. All right. So that's my ketone. And now that's my nucleophile. So the first step is simply the nucleophilic attack. All of these reagents, remember, are strong nucleophiles. And understanding the mechanism help me predict products. So first you're going to be forming, I'm going to write this like that, the phenyl ring. And I'm going to do, after adding the phenyl, so I'm going to have here O negative. I have added another phenyl, which is this, and I have an ethyl group. So again, that's my oxygen, an ethyl right here. I had a phenyl originally, I added another. So the last step would be simply to protonate. And so first step is nucleophilic attack. Second step, proton transfer. So, and you will have the final product is a tertiary alcohol. So from ketones, Grignard gives you a tertiary alcohol. If it is an aldehyde, you will have a secondary alcohol. And here you're adding R groups, whatever the R might be. And when you do the hydride, your nucleophile is a hydride, so you're adding H's. Okay, we're going to keep working on this type of problem. And again, try to understand the mechanism. What is the nucleophile? What is the electrophile? Here, electrophile is the carbon. This is delta positive. This is delta negative. Remember that this is a dipole. So the interaction is nucleophile, electrophile.